Previously, when we were looking at a function like this, we were saying this function has multiple maxima and multiple minima. But what we mean by this exactly is that this function has multiple local maxima and multiple local minima. What does it mean, local maxima, minima? Essentially, if you consider point A, that's a maxima, and this is a local maxima, which means that if we just move away from point A, a little bit to the left, a little bit to the right, and create a neighborhood of this point, let's say I pick up a neighborhood from the one red line to another red line. In this neighborhood, point A is maximum. So if there is a neighborhood of point A, we go a little bit to the left, a little bit to the right, and in this neighborhood, the point A is maximum, that point is a local maximum. In a similar way, we define local minimum. On the other hand, for this particular case, for this particular function, if we change our neighborhood, we extend it. Let's say we take the neighborhood like this. We'll quickly find out that point A is not a maximum of this function over whole space from one red line to the other red line. And really the point B, this point, is going to be a maximum of the point where the function reaches the largest value on this new interval. And such a point will be called a global maximum on specific interval. Let's consider a specific example. Y equals x squared, simple parabola. If we look at the interval from minus to plus infinity, which is basically all values on the horizontal axis, we'll find this function has a local minimum, and that's the only minimum it has, so it's going to be a global minimum at point O for x equals to 0. On the other hand, if you try to find a maximum of this function on this interval, we'll be disappointed because the function doesn't have a maximum. And the reason for that is, well, this function is actually goes up, increases without any limits. When x start going to plus or minus infinity, our function is going to go to plus infinity. The picture is a little bit different if we look at the closed interval from minus 2 to 1, the interval between those vertical red lines. Now we call it closed interval is because the point minus 2 and point 1, the boundaries of this interval, are included in this interval. So here the minimum is still the same. It's x equals to 0. But now we do have a maximum at the point A. That's the point on this interval. It reaches at the boundary, and that's the point where the function has the highest value on whole interval. And in general, the truth is that if you have a function that is continuous, meaning that it doesn't jump anywhere, and we are looking at this function on a closed interval, this function will have a global maximum and global minimum. Now, this maximum and minimum may be reached somewhere in interior points of this interval, or, like in this case, the maximum is reached on the boundary. Now, when we're looking for points of maxima and minima in the interior of the interval, we're going to do it in the same way as we did before. We will calculate derivatives. We'll find the points where derivative is 0 or doesn't exist, and analyze those points to find which point gives us the maximum value, which point gives us the minimum value. But when we talk about closed intervals, we also need to look at the boundaries, because our maximum and minimum could be achieved at the boundary. And at the boundary, as you see in this case, derivative doesn't have to be 0. It could be anything. So we should be more careful. Let's consider an example. The example in this case is a cubic polynomial, written here. And we are looking at the maximum of this function on a closed interval from -5 to 5. So what we're going to do in this case, well, we're going to take a derivative. And derivative of this function is a quadratic function, quadratic polynomial. Well, this polynomial is defined, has a finite value everywhere on this interval from -5 to 5. So there's no points where this function doesn't exist. But there are points where this polynomial is actually equals to 0, where derivative equals to 0. And the roots of this quadratic polynomial are -3 and 2, which means that this function can be written as a product of two linear factors. So the next thing you want to do, you want to analyze this derivative as before, where derivative greater than 0 and where derivative is less than 0. So let's look at our horizontal coordinate. We're going to put those points where derivative equals to 0, those called critical points, -3 and 2. And also we're going to put a point -5 and 5, which are the boundaries of this interval. And now let's look at the sign of the derivative. When x is less than -3, both of these factors are negative. So when we multiply negative factor by another negative factor, we get positive number. And it means the derivative between -5 and -3 is positive, which means the function is increasing. Now if we go to the right of my point -3, between -3 and 2, the first parenthesis is positive, the other is negative, so positive times negative is a negative. So derivative here is negative and the function goes down. Once we pass point 2, both of these factors become positive, derivative is positive, and function goes up. So now what we see that the point of -3 is the point of local maxima, and 2 is local minimum. But now we are not interested in local maximum and local minimum. We're interested is actually global maximum and minimum. So when it comes to global maximum, we see that there's a chance that global maximum is achieved in the same place where a local maximum is achieved, at x equals to -3. But there's also a possibility that the global maximum is achieved at 0.5. So where is it? That's a good question. In a similar way, when we look at the minimum, there is a question. Is it point -5 or 2? Again, we need to figure it out. And the way to figure it out is just to look at the value of this function, cubic polynomial, at those points. So when we look at the maximum, we look at the value of function at -3 and at 0.5, and we see that the function is larger when x equals to 5, which means that x equals to 5 is a global maximum. Now, when it comes to minimum, we can look at the point -5 and 0.2, and we find at 0.2 we have a lower value. It means that 0.2 is our global minimum. So as you see, global maximum is not achieved at the point where local maximum is achieved. It's achieved at the boundary. But global maximum and local maximum coincide. And now we can actually draw a whole function and see how it's going to look like. Function is actually going to look like this. And that also tells us something interesting. It tells us that the function has to cross horizontal axis at 3 points. And it means that this function has 3 real roots. Let's look at another example. And here we have a function v, that's the function of argument t, and that function is defined piecewise, which means that instead of having one formula for a whole range of t, we will have several different formulas for different ranges. Now in this particular case there are 2 ranges. One range is when t is between 0 and tm. In this case the function is at over 2. It's a linear function of t. And another range is when t is between tm to 2tm. In this case the formula is more complicated. Now in this formulas s and a are constants, positive constants, and tm is defined using this formula as a square root of s over a. And what we are asked to do is to find such value t, which we call tau here, where this function reaches the maximum value on the interval from 0 to 2tm. Now before I want to go into the solution, I want to discuss a little bit where this function is coming from. There is a link in the description to this video to another video I made earlier, and that video discussed physics problem. And if you watch that video, you will realize where this function is coming from. But now let's go and solve it. First of all, let's look at this function itself. Let's analyze it a little bit. You see that this function is linear between 0 and tm. So a linear function is continuous. It doesn't jump anywhere. Now, if you look at another interval from tm to 2tm, this function is also continuous. It doesn't jump anywhere. The only place where the function has singularity is t equals to 0, because in this case we would be dividing by 0. But that disaster is avoided because we are taking t greater or equal than tm, which is a positive number. So we're never getting to t equals to 0. Now, so we see that the function is continuous on the intervals from 0 to tm and from tm to 2tm. But now the question is, what's going on at actual point tm? And now if you plug tm instead of t in the top formula and in the bottom formula, we'll find that we're going to get the same answer. So, which means that the function does not jump when it goes through point tm. And the function is continuous in that point as well. Now, the next thing we're going to do, we're going to take a derivative to see where the function goes up, goes down, and where the maximum could be. And again, since the function is a piecewise function, our derivative is also going to be piecewise. We're going to calculate the derivative separately on one range and on the other range. And that's what we're going to get when t is between 0 and tm. We have a constant derivative, and that makes sense because the original function was a linear. And on another range, the function is more complicated, derivative is more complicated. That looks like this. Now, one thing to notice is if we look at both of these functions at t equals to tm, we'll find that both formulas are going to give us derivative equal a divided by 2. So this function v is not simply continuous when it goes through point tm, it also has a continuous derivative when it goes through that point. It means this function is not just continuous, it's also smooth function. All right. Well, the next thing we want to do, we want to analyze this derivative on both intervals, on interval from 0 to tm and interval from tm to 2tm. Now, the first interval, we see the derivative is constant. It's positive because a is positive. So it means that the function itself, function v, is increasing in this interval. And again, that makes sense. You can see directly from this function. It's a linear function with positive coefficient, positive slope. This function is actually increasing. So we're going to have a value of 0 of v at t equals to 0, and then we're going up until we're reaching the maximum value at t equals to tm. And then the function changes. Then the derivative becomes more complicated. Again, as I said before, you can verify it yourself at t equals to tm. The bottom formula gives us a over 2. Now, if you look at the formula below, we find there's a term which s over t squared minus a constant equals a over 2. Now, the first part, s over t squared, is actually going down. It's decreasing when t is going up. And what happens, the whole function is also going down. It's monotonically going down. So the maximum value of the derivative is at t equals to tm. And it's going to go down. And what we find, it's easy to see, when t goes to infinity, the first term goes to 0. And our derivative becomes minus a over 2, which is negative value. So what it means that at one end, the derivative is positive. If I go to high values of t, large values of t, derivative is negative. And it means that somewhere in between, the derivative has to be 0. And let's say that's the point t equals to tau. So before the point tau, between tm and tau, the derivative is positive, the function goes up. And once we pass the point tau, the derivative becomes negative, and the function is going down. Now here I want to make a comment. If you see here, on this plot, I put tau between tm and 2tm, but we didn't really show it yet. So from just simply looking at what I just said, this tau potentially could be beyond t equals to 2m, okay? But to figure out where this tau is, well, let's just find where it is. And it happens to be when the derivative is 0. So s of t squared minus a over 2 equals to 0. And it's not difficult to see that t is the square root of 2s over a. Now, this value is less than 2tm, which equals to 2 times square root of s over a. Okay? So I did put this point in the correct spot. So, and really the only thing is left here to do is to actually draw the function itself, the way it's going to look like. And the way it's going to look like is this. So between 0 and 2tm, the function is growing up linearly. And past tm, the function is still increasing for a while until it reaches the point tau, and then it goes down. And obviously, t equals to tau is the global maximum of this function.